In our last video for the day, we're going to talk about testing to see whether a series converges or diverges. In other words, what we're going to try to determine is when you add up all of the terms in a series, does it approach some number or not? Now, there are some series where it's going to be straightforward to find an expression for the nth partial sums. So let's suppose that we know that the nth partial sum, which is, remember, the sum from k equals 1 to n of an, has some nice simple expression like perhaps 1 minus 1 over n plus 1. I think we found that in a previous example. If we know that, then it is straightforward to actually find what the series approaches. We just take a limit as n goes to infinity of Sn, and that will give us the answer. So in this particular example, we had, we had 1 minus 1 over n plus 1. Well, as n goes to infinity, this thing wants to approach 0, so we're left with just 1, which means that particular sum with partial sums 1 minus 1 over n plus 1 must converge, and it converges to 1. Okay, so if we can find Sn in closed form, meaning we can find a nice simple formula for the partial sums, then the series, which I'll use S to denote the thing that it approaches, is just the limit as n goes to infinity of Sn. Unfortunately, it's not always going to be possible to find a nice formula for the partial sums. Next class, we will look at a couple of cases where it is possible, but most of the time we'll see that it isn't, which means we're going to need to be able to tell whether a series converges or not based on some other test. And the very first and the very simplest test that we can actually use for this is called the nth term test. All right, now the nth term test is the easiest test that we will learn in this unit, but it's also one that is very common for students to mess up. So I want you to pay very close attention over the next couple of minutes. So here's what the nth term test says. It says that if an does not approach 0, then the sum of an diverges. Okay? So if the terms in the sum are not getting smaller and smaller and smaller, if they are not getting closer and closer to 0, then we can conclude that the sum diverges. Okay? So as an example, suppose that we have the sequence an is equal to n over n plus 1, and we want to tell whether the series that's generated by that sequence converges. Well, the nth term test can be useful for answering that question. Notice, if we take a limit as n goes to infinity of the terms, notice we're not taking a limit of the sum, we're taking a limit of the individual terms that we're adding up. In this case, what is that limit? Well, you could imagine dividing the top and the bottom by n. We're essentially multiplying by 1 there. And if we do that, we'll now have a limit as n goes to infinity of 1 over 1 plus 1 over n after multiplying through. And notice now, as n goes to infinity, we'll see that this goes to 0. And so we're left with just 1. And so the individual terms, the things that we're adding up, are approaching 1. And so when we think about our series, it behaves something like the following. We're adding up a bunch of things that are close to 1. So it's like adding up 1 plus 1 plus 1 plus 1. and just doing that forever. Well, is that going to approach any particular number? Well, if I keep adding 1 over and over again, notice the sum gets bigger and bigger and bigger. And so there's no way that that could possibly approach any number. It's just going to grow and grow without bound. And so the nth term test says, since an does not approach 0, the sum diverges. Okay? So this is very, very important. This test only tells us whether something diverges. It does not tell us whether it converges. And so in this case, because we know the terms do not approach 0, we can conclude that the series diverges. But what it does not say, this is a big warning. You need to box this, star this, highlight it, whatever you do to remind yourself of it. This is important. If the limit of an is 0, so if the terms approach 0, we cannot conclude that the sum converges. Okay, so the nth term test goes one way. It says if the terms don't go to 0, it diverges. If the terms do go to 0, then this is going to be inconclusive. So you just shrug at that point and say, this doesn't help. I need something else to help me answer the question. Okay, so to see why this is an important distinction to make, let's look at another example. Let's consider the sum of 1 over the square root of n from n equals 1 to infinity. Okay? And let's think about partial sums here. Well, before we do that, let's think about the individual terms. What happens to an as n goes to infinity? Well, if you take a limit as n goes to infinity of 1 over root n, notice the denominator gets bigger and bigger and bigger. And so we would say that this has got to be getting smaller and smaller and smaller. And it's got to approach 0. So the terms go to 0. Does it converge? Does the sum converge? Well, notice the nth term test is inconclusive on that. It does not tell us whether it converges. If the answer had been that it was something non-zero, then we would know immediately that it diverged. But since we got 0, we don't know. And in fact, what we can show is that this series does diverge even though the terms go to 0. We're adding up smaller and smaller things, but we can still get something infinitely large out of that. And to convince yourself of that, let's think about the partial sums. The nth partial sum is 1 over the root of 1 plus 1 over the root of 2 plus 1 over the root of 3, all the way on out to 1 over the root of n. Agreed? So when we're adding up not all infinitely many terms, but just the first n, we get a sum of all these fractions. And of these fractions, notice that that is the smallest. It has the biggest denominator, so it's the smallest. So what we can say is that Sn is greater than or equal to what we would get if we just added up the smallest term over and over and over again. Okay, so if I take all those fractions and I replace them with something that's smaller, then I should get a smaller answer, right? So the partial sums are bigger than the sum that we've written there. And notice, how many terms do we add up in the original expression? We had 1, 2, 3, all the way up to n. We had n different fractions, which means there are n of those. And so this is just equal to, well, if we're adding up the same thing n times, that's just n times 1 over root n, which is, well, if you take n divided by a square root of n, you just get the square root of n. So these partial sums are bigger than root n. That's something that we've just proven through this brief argument. Well, what does that mean? Well, if the partial sums are bigger than root n, well, what happens to n is, what happens to root n is n goes to infinity. Well, if n is growing, then the radical n is also growing. So since the limit as n goes to infinity of root n is infinity, and Sn is greater than or equal to root n, well, we know right off the bat, this is a scenario similar to what we discussed earlier in the semester. You are bigger than something big, right? The partial sums are bigger than something that's already going to infinity. So we can say that the limit as n goes to infinity of root n is, of Sn rather, must also be infinity. So the series diverges. Okay? So in other words, even though we're adding up an infinite number of things, and even though those things are getting really, really, really small, we're actually adding up to something finite. Well, let's draw a picture to visualize that. So sometimes I like to visualize series by drawing a horizontal axis representing n, and then a vertical axis to represent an, and then we'll draw little dots to represent the individual terms in our sum. So when n is 1, we had the terms we were adding up were 1 over root n, and so the first term is just going to be 1. The next term, when n equals 2, is 1 over root 2, which is around 0.7. The next one is 1 over root 3, which is somewhere in the ballpark of 1/2. And you'll see that the pattern continues. So the individual terms that we're adding up are really just the heights of each of these points above the axis. And what we're saying here when we claim that this sum diverges is that if you were to add up all of those lengths, you'd get something that's infinitely long. The sum of all of the an values is infinitely large. And notice that occurs in spite of the fact that these points are getting closer to 0. Right? All of the terms in our sum are getting closer to 0. So that's a little bit unexpected. But perhaps since we've already talked about improper integrals, this shouldn't catch us completely off guard, because we have seen there are examples of integrals where your width is infinite and the height is getting infinitely small, and we've seen that it is still possible to have something both convergent and divergent that fits that criteria. Okay, so there's one example of a series where the terms go to 0, but the sum diverges. Let's look at one more example. Let's think about the sum as n goes from 1 to infinity of 1 over n, which is known as the harmonic series. And this is a very useful example because it kind of catches you a little bit off guard. It has some surprises in store for us when you look at this series. So let's see if we can determine whether this converges or diverges. Okay, so first off, let's think about our nth term test. The nth term test says that if the terms do not go to 0, then we can stop. We know the answer, it must diverge. So an, the thing that we're adding up, is 1 over n. If we take a limit as n goes to infinity of an, we get the limit as n goes to infinity of 1 over n, which is 1 over something really big, gets close to 0. And so the nth term test tells us well, nothing, right? The nth term test only tells us something if we get something other than 0. This is just going to be inconclusive. Okay, so the nth term test does help us in certain cases, but in other cases it's just going to say, I'm not sure, and this is one of those cases. So unfortunately, we still have not answered our question. So let's see if we can come up with another argument. So let's write down what this sum is. Remember, we were adding up 1 over n from 1 to infinity. So the first term is going to be 1 over 1. The next term is going to be 1 over 2, then 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 8, and I'm going to go on the next line, 1 over 9, and then I'm getting lazy here, so I'm going to skip ahead Eventually, we're going to hit 1 over 16. And then the next one would be 1 over 17. And then notice I'll continue. That continues out. I'll write down 1 over 32, and then 1 over 33, and 1 over 64. And you get the idea. This continues on forever and ever. So the sum has a whole bunch of things. Now, the individual terms are getting smaller and smaller and smaller. And so that's not enough to draw a conclusion here. But there is a way to come to a conclusion by looking at these terms that we're adding up. Because notice, if you group them up in an appropriate way, there is a pattern that emerges. Okay? All right, so let's think about what would happen if we stopped after just one term. After one term, we just have a total of 1. After 2 terms, we have 1 plus a half. Now, the next 2 terms, 1/3 and 1/4, of those two, 1/4 is the smallest. And so these 2 terms, we could say together, that's going to be greater than if we just added the smaller one twice. So that's greater than 1/4 plus 1/4, which is a half. Agreed? So S4, we don't know, I'm not going to write down exactly what it is, but it's greater than 1 plus a half plus a half. Agreed? Okay, well, let's look at the next bunch. Notice there we have 1/5 plus 1/6 plus 1/7 plus 1/8. The smallest of those is 1/8, which means this is greater than 1/8 plus 1/8 plus 1/8 plus 1/8. Well, 4/8 is 1/2, and so we could say that S8 is greater than 1 plus a half plus a half plus 1 more half. And maybe you see where this is going now. Notice, if I think about not the next 4 terms, but the next 8 terms, so now we're at S16, that's going to be greater than 1 plus a half plus a half plus a half plus another half. And then if I look at the next 16 terms, I'll get over another half, and then another half after the next 32 terms. And the point is, I'm basically adding up a half over and over and over and over again. And if you keep adding up a half plus a half plus a half plus a half, what happens to the sum? Well, it grows. It keeps on growing. We can just say exactly how long it will take before it's going to reach 5 or 10 or 100 or 1,000. Eventually, it's going to surpass any one of those things because we know eventually we'll accumulate enough terms so that we've added at least a half from anywhere that we are. Okay? And so what we can say is, let's see, this was 2 to the 1. 4 is 2 to the 2. 8 is 2 to the 3. 16 is 2 to the 4. And it looks like that S2 to the n is greater than 1 plus 1/2 times n. Right? We had 4 factors of 1/2 for the case where we had 2 to the 4th. And what that means is, if we take a limit as n goes to infinity of the thing on the right-hand side, we get infinity. And so the limit as n goes to infinity of s must be greater than that, or equal to it. So our sum must diverge. So because we're adding up these things that eventually will accumulate another half each time, we can convince ourselves that the harmonic series diverges. Okay, so that is an important fact to keep in mind, and it's a helpful reminder when you think about the nth term test, because if you know that the harmonic series diverges, then right off the bat that shows you that it's not enough to see that the terms goes to 0 to conclude that a series converges, because the harmonic series would be a counterexample to that. The terms get smaller, but the sum is still infinitely large. All right, well, that's it for today. We will look at a couple of special types of series called telescoping and geometric series in the next batch of videos for the next class.